Welcome to the deep dive. Today, we're tackling a topic that really gets people talking, Tesla's full self-driving.
Definitely. It's either the future or, potentially dangerous. Very strong opinions out there.
Exactly. It feels like an all-out war sometimes. Our goal here, though, is to look under the hood, based on what's out there, and really try to understand what FSD actually is.
Right. So first things first, let's just clarify the terms. FSD, full self-driving, that's Tesla's brand name for their most advanced driver assist features.
It's the step up from autopilot, basically.
Precisely. Autopilot is their standard 80, their advanced driver assist system. And, other companies have their own names. GM has Super Cruise, Ford uses Blue Cruise, Honda Sensing, lots of different terms for similar tech levels.
And that name, full self-driving, it really paints a picture, doesn't it?
Oh, absolutely. A robot chauffeur, right.
Yeah.
Takes you from A to B, no effort.
But, and this is crucial, right now, that chauffeur needs you, the human, paying very close attention, ready to grab the wheel any second.
That's the critical point. The car attempts to drive itself, yes, but it's absolutely not full-time kick back and relax autonomy. Not yet.
Okay, so the core of our deep dive today is how these cars are trying to do this self-driving thing.
And central to that is their reliance on computer vision, or Tesla vision as they call it.
Especially after they made that big decision to remove radar. And LiDAR was never really in the production plan, and even ultrasonics are gone now on newer models.
Exactly. So the car is basically navigating purely based on what its cameras see. 8 cameras strategically placed around the car.
8 cameras. Okay, let's dig into the seeing part. I think initially people assumed it was processing like 8 separate video feeds in real time.
Yeah, that was a common thought. And that sounds incredibly complicated on its own.
Right.
But the current understanding is a bit different. The FSD computer actually takes those 8 streams and merges them, stitches them together into a single coherent 360-degree panoramic view.
A single view. Wow. And what does it do with that view?
Well, this is where it gets really interesting. It doesn't just display 8-stitch photos. It converts that panoramic video feed into a 3-dimensional vector space.
A vector space?
Yeah.
What does that mean practically?
Think of it like creating a virtual map, a digital twin of the car's surroundings in real time. It digitizes the world into this structured format that the car can then use to understand and navigate, a sort of perfect analog of reality, but one the computer can process.
Okay, I can see how trying to manage 8 separate feeds would be a nightmare.
Oh, definitely. Imagine trying to perfectly line up 8 different perspectives.
Yeah, seams, distortions.
Exactly. Seams where the images meet, different lens distortions, slight perspective shifts just from tiny manufacturing differences between cars.
So the car's brain would get this kind of messy, inconsistent picture.
Pretty much. A jagged and jittery representation, as some have described it. And that likely contributed to some of that hesitant, sometimes jerky driving people experienced in earlier FSD versions.
Right, okay. So this new unified view approach, how does it technically work? How does it overcome those issues?
So each of the 8 cameras is shooting video at 1280 by 960 pixels.
Okay.
And it's 12-bit high dynamic range, HDR, which is important. It helps see details in really bright skies and dark shadows at the same time. Critical for driving.
Makes sense.
And this is happening fast, 36 frames per second.
36 times a second.
Yep. And the FSD computer takes all 8 of those incoming frames and stitches them together into that single seamless 360 composite view in real time, basically 0 lag.
Wow.
And it has to redo that whole stitching process 36 times every second as the new frames come in.
That sounds like a ton of processing power. The stitching part reminds me of, the panorama mode on my phone camera.
Exactly. That's a great analogy. You sweep your phone, it takes multiple shots, software blends them, looks like one photo.
Or those 3D virtual house tours.
Yeah.
Matterport scans, I think they're called.
Precisely. Similar concept. Capturing many images, stitching them into a navigable 360 space. Tesla's doing that constantly, on the fly. The result is meant to look like one shot from one magical camera, not 8 separate images pieced together.
And this unified view gives the car a totally different perspective.
Right.
Not 8 separate little windows, but one big picture.
Exactly. It effectively creates a top-down perspective, often called a bird's eye view, kind of like looking down from a satellite, like Google Earth.
Okay.
And when that seamless image gets converted into the vector space, that digital map.
The lines are smoother. the representation is more consistent.
That's the idea. Smooth, consistent lines, a more coherent understanding of the world, which should lead to smoother, more confident driving.
Okay, so it's got this clear 360 view stitched in real time.
Right.
But driving isn't just about now, it's about anticipating.
Right. And what's really clever here is that the system isn't just looking at the present moment, it considers temporal context,
Yep.
meaning it factors in what it saw just a moment ago, what it sees right now, and even what it predicts might happen next, all at once.
Ah, okay, so if, like, a car blocks its view of a pedestrian for a second.
It doesn't just forget the pedestrian exists. It has this short-term object permanence. It remembers they were there and assumes they probably still are, even if hidden momentarily.
That makes sense. You wouldn't want it slamming the brakes every time someone steps behind a pole, so it remembers objects. What about the road itself? The environment?
Good question. It has spatial memory, too. It retains information about the static stuff where the curbs are, the lane lines, signs, even after they're out of the immediate camera view.
So, like, if it sees an arrow painted on the road for a turn way ahead.
It keeps that arrow in mind, so to speak, in its digital map all the way through the intersection, even if it stops at a red light first. Those markings and signs, maybe 50 meters before a turn, they're super important for predicting how traffic should flow.
So it's remembering what was there and using that memory to anticipate what's coming based on those persistent cues, like road rules embedded in the environment.
Exactly. And it goes further. For every object it puts into that vector space, every car, cyclist, whatever,
Yeah.
it runs predictions. What might this object do next? Based on its distance, its speed, a whole list of potential moves.
So it's constantly calculating probabilities for every other driver on the road.
Essentially, yes. It's trying to anticipate their actions. As things get closer or situations change, it refines those predictions, trying to make a really good guess about what's most likely to happen next.
Okay, wow. And then all of that, the stitched view, the memory of the road, the predictions about other cars, plus traffic lights, signs, that all feeds into the paths the car chooses.
That's the core of it. That whole complex calculation informs the decision-making process, which is driven by artificial intelligence, deep neural networks specifically.
Right, the AI, the brain. And that's
Yeah.
where, a lot of the discussion and maybe the controversy comes in. So how does this AI actually learn to drive? The world's incredibly complex.
Well, fundamentally, Tesla trains it by feeding it just massive amounts of video. That 360-degree video we talked about, captured by their fleet driving in the real world.
Learning by watching?
Pretty much. The AI learns patterns by seeing countless examples of how humans handle millions of different situations. It's kind of analogous to how something like ChatGPT learns language by processing billions of words from the internet.
Okay.
The goal is similar. Train an AI to drive by showing it an absolutely enormous visual data set of driving.
But, anyone who drives in rush hour knows reality isn't always neat and tidy like the rules of the road suggest. It's chaotic.
That is a huge challenge. Theoretical rules are one thing, but actual driving, especially in busy cities, it's messy, unpredictable.
So FSD needs to be trained on everything, every crazy thing that could possibly happen.
Ideally, yes. Every insane, unpredictable scenario, as you put it. Think about the weirdest thing you've ever seen on the road. Now imagine teaching a computer how to react to that safely and appropriately. It's a monumental data and training challenge.
It really feels like Tesla's whole approach, their vehicle design, has been pointing towards this autonomous future for a while now.
I think that's fair to say. Looking back, the hardware choices, the software architecture, it seems clear that current Teslas are built with eventual autonomy as the goal. Musk has talked about an integrated robotic chauffeur.
A chauffeur that learns, maybe even adapts to my driving style.
That's the vision, that the car learns over time, maybe gets better at anticipating your specific routes or preferences, needing less and less human input.
So for my regular commute, the dream is the car just handles it, start to finish, no intervention.
That's the ultimate goal for predictable routes. And for people with more dynamic schedules, the idea is it syncs with your calendar, figures out where you need to go, and drives you there autonomously, point to point.
Which implies that eventually, the legal stuff changes. The need for hands on the wheel, eyes on the road, that could go away.
That's the logical endgame, yes. I mean, think about the hardware inside current Teslas. They have this incredibly powerful processing setup, AMD Ryzen chips, RDNA2 graphics,
Yeah.
basically PS5 level gaming capability.
Right, way more than you need for maps and music.
Exactly. It strongly suggests the hardware is there for much more demanding future tasks. Tasks like full self-driving, maybe even letting occupants, kick back and play games while the car drives.
So when someone buys FSD today, they're not just getting the current features, they're kind of placing a bet.
In a way, yes. An investment in that potential future, putting money down on the belief that this autonomous reality will eventually arrive.
Okay, so let's pivot back to the now, the supervised nature of FSD today. You mentioned a table summarizing the inputs and outputs.
Now, let's break that down. It helps simplify things. So on the input side, what the car uses. First, the sensors.
The 8 cameras, obviously, seeing cars, people, lights, everything. 360 view.
Right. Then ultrasonic sensors, mainly for short-range stuff, measuring distances to obstacles like parking.
And radar, if the cars still have it.
Correct. If equipped, radar helps track speed and distance of moving objects further out.
Okay, sensors, then AI and mapping.
Here we have the neural networks trained on all those video clips doing the prediction braking, turning, etc. And then GPS combined with high-precision maps, which are sometimes used to help follow the navigation route accurately.
And crucially, driver input is still an input, right?
Absolutely essential. Steering wheel sensors detect if your hands are there, ensuring you're paying attention. And of course, the pedals, accelerator, and brake allow instant human override.
So all those inputs feed the brain and the outputs. What the car actually does.
Pretty straightforward actions. It steers, it accelerates, it brakes.
Changes lanes, stops at lights.
Yep, changes lanes when it deems it safe, stops for red lights and stop signs. Basic driving maneuvers.
And under safety.
Key things are driver monitoring using that cabin camera and the steering sensors to check if you're alert. And emergency collision avoidance, the automatic braking if it detects immediate danger.
But the big takeaway, underlined basically, is supervised.
Critically important. Despite the name, the human must watch, must be ready to take control instantly. It's still very much a partnership.
Okay, this brings us back to that vision-centric philosophy, relying primarily on cameras. Why did they go that route when others use LiDAR and radar more heavily?
Well, the core argument from Tesla's side is that vision, the camera data, provides incredibly rich information. Color, texture, subtle visual cues that help us understand depth and context.
Like humans do, we drive primarily with our eyes.
Exactly. The idea is if humans can drive safely with 2 eyes, a sophisticated AI with 8 cameras covering 360 degrees should, in theory, be able to gather enough information to do the same, or even better eventually.
But ditching LiDAR, which gives correct distance measurements, and reducing reliance on radar, that puts a huge burden on the computer vision system.
Massive burden. It has to infer depth, figure out velocity, understand the 3D structure of the world, all from 2D images.
And do it reliably in rain, fog, weird lighting, tunnels, everywhere.
Precisely. Across all conditions, the performance, the safety of autopilot and FSD hinges entirely on how well that vision system can interpret the world.
And that's where supervised learning comes in as the main tool.
It's the foundation, yes. Supervised learning is how they train those deep neural networks. You feed the network tons of sensor input, mostly the camera image sequences,
Okay.
and you also feed it the correct answer, the labeled output, often called ground truth.
So showing it examples, like this is a car, this is a lane line, that light is red.
Exactly. Detecting and classifying objects, identifying lanes and road boundaries, recognizing traffic signals and signs, estimating distances and speeds. The network learns to map the visual input to these correct answers by seeing millions, maybe billions of labeled examples. It learns the what and where from this massive library.
So it figures out what's out there.
Mm-hmm.
But as we said, perception is just step one.
That's right. It's absolutely foundational, but it's just one piece. The perception module creates this understanding of the current scene.
And that understanding gets passed on.
Yep, it feeds into other modules. Prediction, trying to figure out what other cars will do. And planning, deciding the Tesla's own best path and actions.
So the seeing part informs the thinking and acting parts.
Perfectly put. And while those later stages might use other AI tricks, their success totally depends on the quality of the perception input. Garbage in, garbage out, basically. Better seeing enables better thinking and acting.
Now, training these things needs data. Lots and lots of data. And Tesla has a pretty unique way of getting it right. The fleet.
Absolutely. This is a huge advantage. Their global fleet of customer cars acts like a massive distributed data collection network,
Millions of cars, all with the same cameras.
driving in every imaginable condition all over the world. It gives them access to a scale and variety of data that's incredibly hard for companies relying just on dedicated test fleets to match. Every car is constantly recording video, acting like a mobile sensor.
That's the raw fuel for the training.
Exactly. And the sheer diversity is key. Seeing weird intersections in Italy, snowy roads in Norway, chaotic traffic in LA, it helps make the models more robust, better able to handle things they haven't seen in exactly the same way before.
But the amount of raw video must be staggering. Terabytes, petabytes. How do they even manage that? They can't possibly upload everything.
No way. That's where smart data selection comes in, especially with their shadow mode.
Shadow mode, how does that work?
Okay, so imagine a new experimental version of the FSD software is running silently in the background while you're driving normally.
Okay, I'm just driving. The software's watching.
Right. It's processing the sensor data, making its own decisions about what it would do, but crucially, it's not controlling the car. You are.
So it's practicing in secret.
Kind of. But the key is, it's looking for disagreements. Situations where its plan differs significantly from what you actually do.
Like if I suddenly brake hard and it didn't expect that.
Exactly. Or if you swerve or take an exit it didn't anticipate. When there's a notable difference between the shadow model's intention and the human driver's action, that triggers an upload.
Ah, so it sends back just those tricky bits, the problem spots.
Precisely. A short snippet of data video, maybe other logs from that specific event. It focuses the data collection on the edge cases, the situations where the current system might be weak or confused.
That's clever. It's not just collecting data randomly, it's targeting the weaknesses.
Right. It creates this really efficient feedback loop. Deploy a model, maybe in shadow first, identify its failures in the real world via these triggers, collect the relevant data, use that data to retrain and improve the model, then deploy the update, often over the air.
A continuous cycle of learning from real-world mistakes or near misses. Okay, so they get this targeted data, but it's still raw video. How does it become the labeled data the AI needs? The ground truth.
Yeah, that's the next massive hurdle. Labeling. The quality of the training data is paramount.
Imagine initially it was just people clicking on cars and videos.
Pretty much. Manual annotation. Humans painstakingly labeling objects, lanes, signs, frame by frame. But as the data exploded...
It just doesn't scale. Too slow, too expensive, probably inconsistent too.
Exactly. Manual labeling became a huge bottleneck. So Tesla, like others in the field, had to invest heavily in auto-labeling.
Auto-labeling. The computer labels itself.
Not quite itself. It's more like using powerful offline computer algorithms to automatically generate the labels for the raw data. These algorithms can use more processing power and more context than the car has in real time.
Like looking at the video forwards and backwards, or data from other cars.
Exactly. They can analyze sequences over time, combine data from multiple passes through the same area, maybe even use data from simulations. Techniques like structure from motion or multi-view stereo can reconstruct accurate 3D geometry offline, which then helps automatically create precise 3D labels.
Yeah. Sounds way more efficient. So what are the human labelers doing now? Just checking the computer's work?
Largely, yes. Quality control is huge. Verifying the auto-generated labels, handling the really tricky edge cases the algorithms mess up, and importantly, providing feedback to improve the auto-labeling algorithms themselves. It's a human-in-the-loop system, keeps the quality high while scaling up volume.
And I've heard about 4D labeling. What's the fourth dimension? Time.
Exactly, time. Traditional labels might just say car here in 3D space at one instant. 4D labeling aims to capture how things move and change over time.
So tracking its path, its speed, whether it got blocked from view.
All of that. Annotating the trajectory, estimating velocity, acceleration, tracking identity, even when occluded. Trying to label this manually at scale would be insane. Auto-labeling pipelines are crucial for generating this rich 4D ground truth.
Why is that 4D data so important?
Because if you train the models on data that includes motion information, the hope is they can learn to perceive and predict the dynamic aspects of the world more accurately right from the start.
Okay, incredibly detailed data. And then there's this vector space representation you mentioned earlier. Can we unpack that a bit more?
Right, vector space. The idea here is to move beyond just outputting a list of detected objects, like car here, pedestrian there, light is green.
Okay.
Instead, the goal is for the neural network to predict a single, unified, holistic representation of the entire scene, all embedded within a continuous mathematical space, a vector space.
So it encodes everything together, geometry meaning motion, all in one structure.
That's the ambition. The precise 3D shape and movement of cars, the smooth curves of lanes, the state of traffic controls, all interconnected in this common format. Often this involves projecting all the camera views into a shared reference frame, like that bird's eye view or maybe a full 3D grid around the car.
And the advantage is it simplifies things for the next steps, prediction and planning.
That's the hope. A more complete, temporally consistent understanding of everything happening should make it easier to predict what's next and plan the car's path safely and efficiently. But, again, creating the labels for this kind of complex, unified representation relies heavily on those advanced auto-labeling capabilities.
The push for better representations drives the need for better data labeling. Makes sense. So with this data, what kind of AI models, what network architectures are they actually using?
They've evolved over time. An earlier approach often mentioned was the HydraNet.
Hydra, like the mythical beast, multiple heads.
Exactly. You have a shared body, a backbone network that processes the images and extracts general features. Then it splits into multiple heads, each specialized for a specific task.
One head for cars, one for lanes, one for lights.
Something like that. The benefit was efficiency share the initial computation. But the downside could be task interference. Maybe optimizing the backbone for detecting cars hurts its ability to see lane lines perfectly.
Okay, so that was earlier. What about more recently?
Two big trends are occupancy networks and the use of transformers.
Occupancy networks. Sounds like they figure out what space is occupied.
Pretty much. Instead of just finding objects, these networks try to classify every single point in a 3D grid around the car. Is this point occupied by something? Is it free space the car can drive through, or is it unknown?
That sounds much more detailed, a full 3D map of what's solid and what's empty.
Exactly. It gives a really rich geometric understanding, which is super valuable for a vision-only system that has to figure out 3D from 2D. And training these heavily relies on supervised learning with ground truth from those auto-labelers we talked about.
And transformers, weren't those originally for language, like understanding sentences?
They were. That's where they made their big splash. But they've turned out to be incredibly powerful for computer vision, too.
How so? What makes them good for seeing?
They're really good at modeling relationships between different parts of the input, even parts that are far apart. So in driving, they can help fuse information from multiple cameras effectively, figure out which views are most important. They can also model how things change over time, which is key for understanding motion within that vector space idea.
So they help connect the dots, both spatially across cameras and temporally across time.
That's a good way to put it. Their ability to capture context makes them really well suited for the complex task of inferring so much from just camera data.
It really seems like the choice to go vision only is forcing them to innovate heavily on the AI architecture side.
I think that's undeniable. Without LiDAR's direct measurements, they have to develop these more sophisticated ways, like occupancy nets, to understand 3D space. They need things like transformers to make sense of the complex relationships in the camera data.
And these complex models then demand more data, labels, more computing power.
Exactly. It's this tight cycle. Vision only drives architectural complexity, which drives data and compute needs.
Okay, so just to quickly recap the jobs these supervised networks are doing.
Sure. Core tasks include, obviously, object detection and tracking, finding cars, people, bikes, estimating their speed, lane prediction, figuring out the road geometry, traffic control recognition, lights and signs.
Depth estimation is huge for vision only.
Crucial, whether it's an explicit output or implicitly learned by occupancy networks. Also, free space segmentation, where is it safe to drive, and even short-term motion prediction feeding into that vector space. It's a lot.
Training these enormous complex networks on petabytes of data that must need serious hardware.
Oh, absolutely. It's computationally brutal. Initially, they used large clusters of GPUs, graphics cards, like many AI researchers.
Standard stuff, just lots of it.
Right. But as the models and data kept growing, they hit limits. Off-the-shelf hardware wasn't cutting it for the speed they wanted, so they decided to build their own.
And that's Dojo.
That's Dojo. Their custom-designed supercomputing hardware specifically built for training these massive FSD models.
What makes it special? Just faster.
It's optimized. The way the chicks connect allows for super high bandwidth and low latency communication between them. Lots of fast memory right on the chips. Even a custom instruction set tailored for the math involved in deep learning. The whole goal is to drastically slash training times.
So faster training means faster iteration, faster improvement cycles.
Exactly. If you can train a new model in days instead of weeks or months, you can experiment much more rapidly, test more ideas, and potentially improve FSD performance much faster.
It's about accelerating that whole development loop. Okay, so they have the hardware. How do they actually measure if the network is learning correctly during training?
That's done using loss functions. These are mathematical formulas designed to measure the difference, the error, between the network's predictions and the ground truth labels in the training data.
So the goal is to minimize that error, that loss.
Precisely. Designing good loss functions is critical, especially for complex outputs like occupancy grids or vector space. The loss might have multiple parts, penalizing different kinds of errors. Then, optimization algorithms, things like Atom, adjust the millions or billions of parameters in the network, nudging them in the direction that reduces the loss. It's how the network learns.
We talked about real-world data being vital, but you can't safely capture everything that way, right? Like really rare crashes or dangerous scenarios.
Absolutely not. And that's where simulation comes in, creating realistic virtual worlds where you can safely generate data for those rare but critical edge cases.
And in simulation, you have perfect ground truth, right? You know exactly where everything is.
Exactly. So simulated data can supplement the real-world data, helping the models learn to handle dangerous situations they might rarely encounter otherwise.
And then shadow mode comes back in for validation, checking how the models perform in the real world before release.
Yep. Shadow mode is crucial for large-scale validation. Running the candidate models silently lets them gather real-world performance data, see where they disagree with drivers, measure prediction accuracy, all before giving the model control of the car.
Okay, so it really is this powerful cycle. The fleet and shadow mode gather targeted real-world data.
Sophisticated auto-labeling creates rich ground truth.
But complex models like occupancy nets and transformers learn from it,
Trained incredibly fast on Dojo,
then deployed quickly via over-the-air updates.
which then feeds more data back into the system. It's a data model compute flywheel, as they sometimes call it. Dojo really greases the wheels of that flywheel.
And that deployment part, the over-the-air OTA updates, that seems like a massive advantage compared to traditional car manufacturers.
Huge advantage. Being able to push significant software updates, including entirely new FSD models, to the whole fleet almost instantly, that enables that rapid iteration we keep talking about. Improvements get to users quickly, and the data from those updates immediately informs the next cycle. It's fundamental to their approach.
Okay. Despite all this incredible tech, this sophisticated process, there must still be limitations, right?
Yeah.
Challenges with relying so heavily on supervised learning for full autonomy.
Oh, absolutely. It's not magic. Supervised learning has inherent limitations. A major one is handling those edge cases, the truly novel, unexpected situations. If something is too rare, it's hard to get enough training data for it, so the model might not generalize well.
The long tail problem, they call it.
Exactly. Then there's the challenge of label quality and scalability. Ensuring accuracy and consistency across petabytes of data, especially for complex things like 4D labels or vector space, is incredibly hard. Errors in the labels can get learned by the model.
And the models can be brittle sometimes, like
Right.
small changes in the input throw them off.
That can happen. If the training data didn't adequately cover certain variations, maybe unusual lighting or weird road markings, performance can degrade unexpectedly.
And maybe the biggest one,
Mhm.
they learn correlations, not necessarily cause and effect.
Yeah, that's a fundamental point. Supervised learning is great at finding patterns in data, but it doesn't inherently understand why things happen. It doesn't build a deep causal model of the world, which might be needed for true reasoning in totally new situations.
So the seeing part, the perception, is critical and incredibly advanced, but it's not the whole story for autonomy. How does it match with the prediction and planning parts?
The perception system provides the input, that structured understanding of the world. Prediction models then take that and try to forecast what others will do. Planning models take all of that and decide the car's actions.
And the quality of the perception directly impacts prediction and planning.
Absolutely. If the perception is inaccurate or incomplete, the predictions will likely be wrong, and the plan could be suboptimal or even unsafe. Those downstream modules might use different AI techniques, maybe reinforcement learning for planning, but they all depend on good perception.
Looking ahead, has Tesla hinted at what's next? Future directions beyond refining this current approach?
They've talked about concepts like end-to-end models, potentially models that learn to map raw sensor input directly to driving controls, maybe bypassing some of the distinct intermediate steps like explicit perception or planning modules, kind of learning the whole driving task in one go.
Interesting. Anything else?
There's also research interest generally in world models, internal models the AI builds to understand how the environment works, its physics, its rules. That could lead to more robust long-term prediction and planning. And of course, just continued scaling bigger models, more data, faster training with Dojo.
So it sounds like getting to level 4 or 5, true autonomy, isn't just about perfecting the vision and perception. It also needs major leaps in prediction and planning, especially for handling all the uncertainty and weirdness of the real world. Supervised learning alone might not get us all the way there.
I think that's a very accurate assessment. The limitations we discussed really highlight why breakthroughs in those other areas, prediction, planning, maybe even causal reasoning, are likely essential components for the final solution.
Wow. Well, this has been incredibly insightful, a real deep dive. So to try and wrap up, Tesla's core strategy is heavily vision-centric, powered by this immense data engine using the fleet and shadow mode.
Right, coupled with advanced auto-labeling for that rich ground truth, sophisticated AI models like occupancy nets and transformers.
All trained super fast on custom Dojo hardware and deployed rapidly via OTA updates.
Exactly. And you can't deny it's been effective. It's enabled some very advanced driver assistance features, and their ability to leverage scale is a huge advantage for iteration. The move towards these rich, unified representations like Richter space shows real sophistication.
But as we hammered home, the road to full level 45 autonomy still has major challenges. Those inherent limits of supervised learning edge cases, maybe causal reasoning, are still big hurdles.
Definitely. Auto-labeling in Dojo helps speed things up, but performance is still ultimately tied to the training data and how well the system generalizes to the genuinely unknown.
So Tesla's journey is this incredibly ambitious, data-driven push on vision-based perception. But ultimate success probably hinges on integrating that powerful perception with breakthroughs in prediction, planning, and handling the truly unpredictable stuff that goes beyond direct supervision.
That seems to be the crux of it. Integrating all these pieces, perception, prediction, planning, and maybe something more like reasoning to handle the full complexity of the real world. It's a fascinating and incredibly complex technological challenge to watch unfold.